You've been told that temperature controls creativity and top P controls diversity. That explanation is technically true, like saying a car moves because of explosions. Accurate, useless, and missing everything that actually matters for operating the thing. Both parameters do the same job on the surface. They restrict which tokens the model considers before sampling. That's it. That's the whole thing. But they restrict in completely different ways. These different shapes of restriction produce completely different failure modes, and almost nobody explains that part. Let's start with the probability distribution. Everything here lives in that distribution. You cannot understand either parameter without it. Every time a language model generates a token, it produces a list of every token in its vocabulary, assigning each a probability. The full list, all 50,000 entries, or however many tokens are in the vocabulary. Most of those probabilities are essentially zero. A tiny fraction are non-zero. A smaller fraction still are the ones that actually compete for the next position in the sequence. Before sampling, the model has done the hard work, processed context, run through transformer layers, applied the final linear projection, and produced what are called logits. Logits are unnormalized scores. To turn logits into probabilities, you run softmax over them. What you get back is a proper probability distribution that sums to one thing. That distribution is shaped by everything the model learned during training. Here is the thing most explanations skip. The shape of that distribution is not fixed. It changes based on context. When the model is very confident about the next token, the distribution is spiky. One or two tokens have almost all the probability mass. Everything else is negligible. When the model is uncertain, the distribution is flat. Many tokens have similar probabilities, and there is genuine competition for the next position. Temperature operates on the logits before submax. Toppy operates on the probabilities after submax. That ordering is not incidental. It determines what each parameter actually does, and why they behave differently under different conditions. Temperature is a divisor. You take every logit and divide it by the temperature value. If temperature is 1, nothing changes. You get the standard distribution. If temperature is less than 1, you are dividing by a smaller number, which makes the logits larger in magnitude, which makes the softmax output more extreme, which sharpens the distribution. High probability tokens get more probability mass. Low probability tokens get less. The distribution gets spikier. The model becomes more decisive, more repetitive, more likely to keep picking the tokens it already considered most likely. If temperature is greater than 1, you are dividing by a larger number, which makes the logits smaller in magnitude, which makes the softmax output flatter. Probability mass spreads across more tokens. Tokens that were low probability become more competitive. The model becomes less decisive, more varied, more likely to pick something unexpected. Push temperature high enough, and the model starts sampling nearly uniformly, and the output becomes incoherent. The critical property of temperature is that it rescales the entire distribution uniformly. Every token gets the same treatment. The relative ordering of tokens stays the same. Temperature changes the confidence, not the ranking. Toppy works differently. After softmax, you sort all the tokens by probability descending. Then you walk down that sorted list and keep adding tokens until the cumulative probability reaches your p-value. Everything below the cutoff gets discarded. The remaining tokens get renormalized to sum to 1. And sampling happens from only those tokens. What this produces is a dynamic vocabulary. When the distribution is spiky, reaching a cumulative probability of 0.9 might only require 3 or 4 tokens. When the distribution is flat, reaching 0.9 might require 50 or 100 tokens. Top P adapts to the current state of the distribution in a way that temperature does not. This adaptation is the whole reason Top P exists. The problem it was designed to solve is that temperature is a blunt instrument. Setting a fixed temperature works fine when the distribution has a consistent shape. But real generation is not like that. Some tokens are obvious. The word that follows an opening quotation mark in formal English is fairly predictable. Some tokens are genuinely ambiguous. In creative writing, after a character has been established, any number of continuations are plausible. Temperature applies the same scaling, regardless of which situation you are in. Top P tries to keep the effective vocabulary size consistent. At high confidence moments, it stays focused on the few tokens that make sense. At low confidence moments, it expands to allow more exploration. You are not fighting the model's natural uncertainty. You are riding it. This does not mean Top P is strictly better. It means Top P is solving a different problem. And because it is solving a different problem, combining them the naive way does not give you independent control. You are applying two filters to the same distribution, and the interaction between them is not always obvious. Here is a concrete example. Suppose you have Top P set to 0.9 and temperature set to 1.5. You have told the model to expand the distribution by increasing temperature, which increases the number of tokens with non-negligible probability. Which means Top P has to include more tokens to reach 0.9 cumulative mass. You have effectively amplified Top P's permissiveness. They compound. You did not get independent controls. You got two things pulling in the same direction and multiplying each other's effect. Now flip it. Temperature at 0.5 and Top P at 0.9. You have compressed the distribution, concentrating probability mass on fewer tokens. When Top P goes to accumulate 0.9 of the mass, it hits its cutoff quickly. Because fewer tokens are holding more mass, Top P becomes nearly irrelevant. The temperature is already doing the restriction, and Top P is just catching up to a cutoff. That's been predetermined by the temperature scaling. Again, not independent. The genuinely independentish regime is temperature near 1.0 with Top P doing the actual work. Or temperature doing the actual work with Top P set near 1.0 to effectively disable it. When you stack non-trivial values for both, you are not tuning to knobs. You are adding two constraints to the same process and accepting that their combined effect is context-dependent and somewhat unpredictable. This is why API documentation that says to use one or the other but not both is not being conservative. It is reflecting actual practice. Anthropic's documentation says this. OpenAI's documentation says it. The models themselves were calibrated with temperature-only tuning in mind for most use cases. Top P was added as an alternative approach, not as a complement. Which one should you actually reach for depends on what you are building. Temperature is easier to reason about when your problem is about output diversity in a general sense. You want the model to be more or less constrained across the board. You are not trying to protect against the model going completely off the rails at low confidence moments. You are fine with a consistent bias toward or against predictable output. Top P is more useful when the distribution shape is variable within your task. Creative generation, open-ended chat, anything where the model alternates between high confidence, boilerplate, and genuinely uncertain creative choices. Top P handles the transitions better because it scales with the uncertainty, rather than against it. Top K is worth mentioning here since it often comes up alongside these two. Top K is a simpler version of Top P. You keep the Top K tokens by probability and throw everything else out. The cutoff is a fixed count, not a dynamic cumulative mass. The limitation is obvious. Top K of 40 means 40 tokens at high confidence moments and 40 tokens at low confidence moments. You lose the adaptive property entirely. Top P is strictly more principled for variable confidence generation. Top K survives in practice because it is computationally simpler. And because for many tasks, the distribution is consistent enough that the difference does not matter. There is another parameter that affects sampling that almost nobody outside of research mentions, and that is min-p. Min-p sets a floor on individual token probability as a fraction of the most probable token's probability. If the top token has probability 0.4 and your min-p is 0.1, any token with probability below 0.04 gets cut. This keeps the cutoff relative to the current best option, rather than absolute. It handles the flat distribution case differently than Top P, and in some evaluations produces more coherent creative output. It is not widely exposed in consumer-facing APIs yet. It exists. It matters for anyone building on locally hosted models, where you have full sampling configuration access. The last thing that is worth knowing is what repetition penalty and presence penalty do. In relation to all of this, because they are also modifying the logits before sampling, repetition penalty reduces the logit of any token that has already appeared in the context. Presence penalty does something similar but typically with a fixed penalty rather than a multiplicative one. These operate on the pre-softmaxed logits, same tier as temperature. If you stack temperature reduction with a high repetition penalty, the two interact. You are sharpening the distribution while simultaneously suppressing the highest probability tokens that would otherwise dominate a sharpened distribution. The result is not well characterized by just knowing the values independently. You have to know the current context and what tokens are being penalized. The practical summary, stripped of caveats, is this. Temperature rescales the whole distribution before sampling, uniformly, affecting confidence everywhere. Top P clips the distribution after the fact, dynamically, based on how the probability mass is actually distributed. Combining them non-trivially creates interactions that require actually understanding both to predict. Most use cases are better served by one primary parameter set meaningfully, and the other set to near default. If you are building something and it is outputting repetitive garbage, temperature is probably too low, or repetition penalty is missing. If it is outputting coherent but dull output, temperature is probably fine but slightly low. If it is outputting wild nonsense that sounds like it fell off the probability distribution entirely, temperature is too high. If it is producing good sentences but occasionally going off topic in ways that feel arbitrary, Top P might be catching edge cases poorly, and dropping to a lower Top P value or adjusting temperature might help. The reason these parameters exist in the form they do is partly principled and partly historical accident. Nucleus sampling, which is what Top P is, was introduced in a 2019 paper specifically because Top P had the fixed cutoff problem, and researchers wanted something adaptive. Temperature has been in language model sampling since the beginning. They accumulated independently. The fact that every major API exposes both does not mean they were designed to be used together. It means the field inherited both and has not agreed on which one to deprecate. You now know more about this than the documentation will tell you. What you do with it is your problem.